A new form of quantization has just been released, and it allows you to generate text with twice the speed and improved precision over GPTQ. It's called Activation Aware Weight Quantization, or AWQ, and today I'll be showing you how to set up a server with just a few clicks for Llama 70B using AWQ. I'll then show you how to run AWQ in a Colab notebook, and lastly, if you want to stay on, I'll give a tiny lecture explaining some of the differences between AWQ, GPTQ, and the original round to nearest type of quantization. The quickest and easiest way to get a server running with Llama 270B or any open source language model is probably using RunPod or a similar service. By the way, if you know of a similar service that I should try out, please let me know. You can grab the affiliate link for RunPod below in the description if you'd like to support the channel. Then you can go over and log in. Once you're logged into RunPod, you can head to Secure Cloud and scroll down here to pick an A6000. I find this is the best trade-off between speed and price. And search now for Trellis Research and find the Llama 70B API. You click Continue and click Deploy. This will deploy an instance of Llama 70B using AWQ Quantization. I have tried it out and it runs about twice as fast as GPTQ, and it should provide better accuracy as well. So here I'll just click down and I'm going to grab the pod ID, which I'll need for setting up chat UI, a chat interface. Now you can also just call this API using a curl request, which I'll show you as well. So I'll head over to this private GitHub repo. You can purchase access below in the description, but I'll give you all the details you need today. If you do want to make a curl request, you'll be able to make those requests to your API using a snippet like this. Just replace your pod ID here, the RunPod ID right there, and make the request through your terminal. What I want to do though is run chat UI. So you would open up a terminal. You can check out one of the previous videos for this in detail. Clone chat UI, start a Mongo database, move into the chat UI folder and install everything that's required with npm install. Then you need to create a .env.local file and open it up. This is where you'll specify some of the model details. I'm going to show you that now. So I'll move over to my terminal and here I'm in chat UI. I'm going to do nano.env.local, and here I have that file specifying the model description. You would then go ahead and paste in all of this here, which specifies the starting and end tokens for the prompt structure, the temperature, and also you'll see here you have to input your pod ID so that chat UI knows what endpoint to hit. So I'll go back to my pod here. I'm just going to copy the ID. And now I'm going to go into nano.env.local. And my head is a little bit in the way here. I'm going to replace the previous pod I had put in with this latest pod. Control X, press Y to save, and enter. And now I'm ready to run chat UI. Once the pod is started, you can check out the logs here. You'll see that the container is started for text generation inference. If you go to container logs, I can see that the safe tensors are being downloaded. This is the bloke AWQ model. It's the 70B version, and it will take just a few moments. So I'll click pause for these 4 files to download so that we have a complete copy of the model. You can see now that all 4 of the model shards have been downloaded. It's roughly about, I think, bit under 40 gigabytes in size for the 4-bit quantized version of the Llama 70B model. And once the shards have been downloaded, they'll just be loaded into the GPU for inference to begin. And you can see actually the GPU memory usage has gone up here, and that indicates that the model is indeed on the GPU. And we have this message saying defaulting to a hostname of 0s, which means that we are ready. So I'm going to head back to my terminal here and I'll do npm run dev. this will initiate the chat UI server. I'll now copy this URL here and head back to my browser. Now I will just visit that chat UI. And here we are. Let's create a new chat. And I'm going to ask it to write an essay on the season of spring. I have my phone here and I'm going to turn on the stopwatch. As I press enter and start generating, I'm going to time the length of this inference. This is a very rough way to get an inference speed. So you can see we're generating the essay here about spring. And let's see how much text it generates. Okay, inference is done here. And what I like to do now is just highlight all of this essay and copy it and go to wordcount.com and paste it in. So that's 459 words. So now what I do is 459 multiplied by 1.25. Sorry, 1.25, because that is to allow for the fact that there are about 1.25 tokens for every word. And then I'm going to divide by the time, which is 52 seconds. And you can see here, my average inference speed is about 11 tokens per second. So 11 tokens per second by running an A600 with a quantized with AWQ Llama 70B model. So I think you'll find that rate of inference, as you could see, it's pretty much reading speed. It would be nice to have a little bit higher, which you can do by running on 2 of these GPUs instead of 1. That will still be cheaper than using an A100. Next up, I'm going to show you how to run AWQ in a Google Colab notebook. Now, there are a few caveats to be aware of in doing this. The major one is that you need to have a modern GPU like an A100. You can see I've selected it here. Unfortunately, the free Colab notebooks with a T4 or even a paid notebook with a V100, they're not able to support the kernels for matrix-matrix multiplications that both give AWQ the speed and allow it to run. If you do choose an A100, which you can do so by going to runtime, change runtime type, and selecting A100 on a Pro or Pro Plus plan, you can then pip install Auto AWQ. And then using the snippet I've included here below, you can run inference. I've currently set up a question: what's the best post-training quantization method for LLMs as of your latest knowledge? And then you can run that by clicking this output cell here. And here you've got an example of the inference and a pretty long answer. So that's a quick overview of running in Colab. I don't particularly recommend it. If you look at the pricing on running in Colab with an A100, it's 13 units per hour, which is about $1.30 per hour. And the A100s that are provided on Colab are only 40 gigabytes. They're not 80 gigabytes. You can see here 40 gigabytes. RunPod, or probably other services too, will provide an 80 gigabyte GPU for just a little bit more, maybe 180 or 190. Or you can run for 70 to 80 cents an A6000, which gives pretty close speed. In any case, Colab can be handy for doing quick experimentation, and you might find it useful. For the last part of this video, I want to explain a little bit how quantization works and how AWQ in particular works. If you do want to get some of the details, I recommend you to look back at the original paper, which you can find here. And you can also check out the GitHub repository, which is available at mit-han-lab. And you can check out some more examples and ways to do inference. The Blokes repository on Hugging Face is also helpful. It's got the models themselves already quantized, and it also has some helpful code that I used in order to do inference in the Colab notebook. So let's start things off and consider a weight matrix and also an input vector, which you can think of as a representation of a word, and then an output activation vector. And as is common in neural networks, you would take the product of the weight matrix and the input vector to get an output activation vector. So here I'm just going to print a made up matrix W that I've made up. So it's 9, 4, and 1 on the diagonal. And let's also print an input vector, which maybe represents a word. It's just 1, 2, 3. To calculate the activation, you would take the product of those two. And so an output vector through that multiplication would be 9, 8, 3 in that example. With quantization, we don't have the same range of numbers to represent each of these numbers. Let's consider a case where we want to quantize to 2 bits. If you have 2 bits for representing a number, that gives you 4 levels, 0, 1, 2, 3. Or you can think of it as 0, 0, 0, 1, 1, 0, and 1, 1 in binary. So very naively, if you wanted to represent a matrix, such as the one here above, using the quantized levels, you could simply round each of these numbers to the levels. So if you do that, I'll just run this script here. You can take the original matrix, which is 9, 4, 1 on the diagonal. 9 will round to 3. 4 will round to 3. It's the closest level available. And 1 will also round to 3, closest level. So a quantized representation of this matrix here would be 3, 3, 1 on the diagonal. Now you can see this is not great because two numbers that are quite far apart, 9 and 4, end up being represented by the same quantized level. So a better approach would be either maybe to somehow slide the 9, 4, and 3 down so that at least you get 9 and 4 mapping to different levels, or you could scale the whole matrix here by some value. Just looking at the levels and given the max level is 3 and the max value in the matrix is 9, it seems like maybe scaling by a factor of 3 if you scale the matrix down. So it would be 3 instead of 9 and 1.3 instead of 4 and 0.3 instead of 1. That would kind of map more nicely onto these levels and maybe give a better representation. So let's do that here. We'll scale the matrix first, and then we'll apply the quantization. So you can see we're scaling by 0.33. So we have 2.97, 1.3, and 0.3. And now when we quantize, this gives a matrix of 3, 1, 0 on the diagonal, which at least looks a bit more similar in shape or magnitudes as the original matrix. And this is what's called RTN, round to nearest. Typically involves a quantization where you do some scaling, and you typically scale based on the minimum and maximum values in the original matrix. You scale that difference so that it maps nicely onto the minimum and maximum values in the levels, which is a range of 0 to 3. Now, you can also choose the scaling factor in a more optimal way. So you can ask the question of, well, okay, I know the scaling based on min and max of the weight matrix, but maybe there's a better scaling factor that we can look for. And the way we know if it's a good scaling factor is we can look at the error. We can look at the difference between the original matrix multiplication of W times V, which is the unquantized matrix, and then we can subtract off the W times V in quantized form. Let me just show you that code snippet here. I've defined the error in the raw versus the quantized as the raw activation, which is W original times V, minus the scaled quantized activation, which is W quantized times the input vector V, and then unscaled. And just for this example where we've chosen a scaling factor of 0.33, you can see the activation error is about 3.6. And just for illustrative purposes, let's set the scaling factor back to 1, which means we're not doing any scaling. Here, as previously, the matrix gets quantized as 331 on the diagonal, and you have a much larger activation error. So clearly scaling helps. Empirically, scaling using the min and max values, the difference in the min and max, and mapping them onto the levels works quite well, as we saw when running this code here with the scaling factor of 0.33. But now with AWQ, what we do is ask the question of how can we pick an optimal S? So rather than using our rule of thumb, like we do in RTN or round to nearest, is there a better way to pick the value of S? And quite simply, we could just map a range of S values and see how the error on the activation varies. Let's do that here actually. I have some code and it outputs a plot where S is varied from 0 all the way up to 1, actually from 0.1 up to 1. And we plot here the activation error. So I'll zoom out a little bit just for this graph. Here we have the plot, and we have activation error and scaling factor. And you can see that there is a global minimum and then there are local minima. It's not continuous because of the quantization levels. You have these kind of sharp corners in the curve. What AWQ is asked, well, why don't we pick S so that it gives us the minimum activation error? That's a really high level explanation. And actually, that is going to be a bit better than using round to nearest, where we use the min and the max to determine what the scaling factor should be. But the round to nearest approach with min and max is quite good. It's not too far from the global minimum. Remember, this is a 3 here on the y-axis. So the difference between using AWQ is a bit better, but not revolutionarily better than the round to nearest approach. So this is kind of a visual representation of AWQ, which is a bit better, and then round to nearest, which is here. Now let's talk a little bit about GPTQ, which you can actually add on top of AWQ. So even when I say AWQ is faster than GPTQ, we'll come on to the discussion of speed, but really they're not exclusive. What GPTQ does is it says, well, let's quantize each of the entries in the weight matrix one by one. And when we quantize the first one, we're going to do a correction on the other ones to balance out any loss that we might have introduced. And the way this is done is by quantizing one weight, running a forward pass with some data, figuring out the error created on the other weights, and then updating those other weights. Then you move to the next weight in the matrix, you quantize that, check the errors created, and update all the other weights. So you progress through the weight matrix every time correcting the remaining weights. So you could do AWQ, in other words, choose an optimal scaling factor, and then do some corrections and iteratively apply more corrections. And this does allow you to get even better performance than AWQ. Now you might say, well, doesn't AWQ give the lowest activation error? And it does, but remember, this is just the activation error for one given matrix or one given layer of the neural network. GPTQ actually looks at the entire network and sees the losses and then makes a correction of the later weights. There's an important discussion here on data dependence. So in order to make corrections with GPTQ, you need to propagate a full data set through to find the losses that you are creating, which means that when you quantize with GPTQ, your quantization is going to be specific in a kind of second order way to the exact data set you quantize on. You could quantize on, this is not exactly right, but let's say dogs, but then have questions on cats. And so you might find that you've got some inaccuracies because you quantized on a data set that's different from what you want to use the language model for. AWQ is also data dependent because it relies on this graph here of activation error versus scaling factor. And the activation error, of course, comes from activations, which comes not just from the weight matrices, but also from the inputs. Remember, activation is W, the weight matrix, multiplied by V, the input vectors, which are the words. So ultimately, this graph depends on the input words and the input data set you use for quantizing. Now, AWQ is maybe a bit more robust because it doesn't do this second order correction or changing of the weights. So there's no risk of the weights being changed because of your quantization data set. The weights aren't being corrected. There's no attempt to correct the weights. You're simply choosing the optimal scaling factor based on the input data set. So the only method that's not data dependent is round to nearest. Although if you know the data set that you want to operate on, you're still going to be better off to quantize with a snippet of that data set, because that kind of fitting is going to result in your quantization giving better results for the data set in hand. However, if you had absolutely no idea what data sets you want to use the model on, perhaps round to nearest might be more robust in some senses. I suspect, in fact, that a geometric type of round to nearest, or maybe logarithmic, might be more robust. Instead of just rounding up or down to the nearest level, you might represent first transform those levels in a geometric way or by taking a logarithm. And that might provide a better scale on which to do rounding than simply what I'm calling the linear type of rounding that's done in RTN. Last off, a few notes on speed. Let me increase again my screen size here. Somewhat confusingly, when we talk about the speed of GPTQ versus AWQ, that doesn't necessarily refer solely to how quantization is done. Both GPTQ and AWQ use quantization. That does provide a speed up because it reduces the size of weights that need to be loaded into the part of the GPU's memory that does computation. And that loading of weights into the GPU is often the bottleneck, particularly on small batch sizes. And so just by doing the quantization, you reduce the size of the matrices that needs to be loaded, and you can reduce the memory bandwidth requirement in order for running the inference. But as I said, that's by and large somewhat similar for AWQ and GPTQ. What differs is the way that the multiplications are set up. AWQ uses matrix-matrix multiplications, whereas GPTQ uses matrix-vector multiplications. And with modern GPUs, the matrix-matrix multiplications are more efficient. And so AWQ kind of leverages one of these, let's say, special features of the GPUs. That's also, I suspect, why I'm not able in this Colab notebook to run AWQ. Maybe there's some way of doing it by specifying some other flags, but the kernels aren't supported on the older GPUs, which is why I was only able to run inference with an A100, or I ran with an A6000 on RunPod. And that's it for this overview of quantization. In short, if you're running on a T4 or a free Colab notebook, you probably want to stick with GPTQ. But if you want to get a server up and running, which possibly is the most cost-effective way to run inference on these models, AWQ will give you a speed up over GPTQ, and it will also provide an improvement in accuracy. For most data sets, it's at least as good as round to nearest, the basic approach for quantization, and often performs better if you know the types of data sets you're going to use the model on. As per usual, you can find some of the links in the description below, some free Colab notebook links, and you can also purchase access to the Trellis Llama server setup repo, which explains in more detail recipes for running inference, including longer context lengths. All right, folks, take it easy.